Hello everyone, my name is Srijit and we are discussing the paper MCAC35 Advanced Database Management Systems. Today's topic is Database System Architectures. The architecture of a database system is greatly influenced by the underlying computer system on which it runs. In particular, by such aspects of a computer system as networking, parallelism, and distribution. Let's see these aspects. First, networking. Networking of a computer allows some tasks to be executed on a server system and some tasks to be executed on client systems. This division of work has led to client-server database systems. Next is parallel processing, which allows a computer systems to speed up database system activities, allowing faster response to transactions as well as more transactions per second. Queries can be processed in a way that exploits the parallelism offered by the underlying computer system. The need of parallel query processing has led to parallel database systems. Then, distributing data across sites in an organization allows those data to reside where they are generated or both needed, but still to be accessible from other sites and from other departments. So keeping multiple copies of the database across different sites also allows large organizations to continue their database operations even when one site is affected by a natural disaster such as flood, fire, or earthquake, or any other disasters or any other man-made disasters, etc. etc. Distributed database systems handle geographically or administratively distributed data spread across multiple database systems. So these are the aspects that led to different database architectures. Now let us discuss the architecture of database systems, starting with the traditional centralized system, then covering client-server, server system architectures, and later parallel and distributed database systems. Centralized database systems are those that run on a single computer system and do not interact with other computer systems. Such database systems span a range from single-user database systems running on a personal computer to high-performance database systems running on high-end server systems. Client-server systems, on the other hand, have functionally split between a server system and multiple client systems. First, let's see the components of a centralized computer system. Modern general-purpose computer system consists of one or two processors and a number of device controllers that are connected through a common bus that provides access to shared memory. The processors have local cache memories that store local copies of parts of the memory to speed up access to data. Each processor may have several independent cores, each of which can execute a separate instruction stream. Each device controller is in charge of a specific type of device, for example, a disk drive, an audio device, or a video display device, etc. The processors and the device controllers can execute concurrently, competing for memory access. Cache memory reduces the contention for memory access since it reduces the number of times that the processors need to access the shared memory. Then we can use the computers in two ways, as a single-user system and as a multi-user system. Personal computers and workstations fall into the first category. A typical single-user system is a desktop unit used by a single person, usually with only one processor and one or two hard disks, and usually only one person using the machine at a time. A typical multi-user system, on the other hand, has more disks and more memory, and many have multiple processors. It serves a large number of users who are connected to the system remotely. The database system designed for use by single users usually do not provide many of the facilities that multi-user databases provides. In particular, they may not support concurrency control, which is not required when there is only one user, because the single user is generating the updates. So there is no need for concurrency control. Provisions for crash recovery in such systems are either absent or it will be primitive. There will be having a simple backup system. Okay. Some such systems do not support SQL and they provide a simple query language. And database systems designed for multiple or multi-user systems support the full transactional features that we have studied before in database management systems. Next, let's see client-server architecture. As the personal computer became faster and more powerful and cheaper, there was a shift away from the centralized systems to a client-server model, where the personal computers become nodes and the powerful centralized system becomes a server, where these nodes connect to the centralized server system as client systems. So the image shows a typical or a general structure of a client-server system. In case of a client-server system, the functionality provided by a database system can be broadly divided into two parts, the front end and the back end. The back end manages access structures, query evaluation and optimization, concurrency control and recovery, while the front end of the database system consists of tools such as the SQL user interface, form interfaces, report generation tools, and data mining and analytics tools. The interface between the front end and the back end is generally through SQL or through an application program interface. Systems that deal with the large numbers of users adopt a three-tier architecture, and some transaction processing systems provide a transactional remote procedure call interface to connect clients to the server. The advantage of replacing mainframes with the client-server systems is that it offers a better functionality for the cost. So it is cost efficient, and it provides flexibility in locating resources and expanding facilities. So you can easily expand these things. You can keep on adding new nodes to the servers. So it provides better user interfaces and easier user interfaces, and it is easy to maintain these client server systems. Let's move to the next part, server system architecture. Server systems can be broadly categorized as transaction servers and data servers. Transaction server systems, also known as or also called query server systems, provides an interface to which clients can send a request to perform an action, in response to which they execute the action and send back result to the client. On the other hand, data server systems allow clients to interact with the servers by making requests to read or update data in units such as files or pages. For example, file service provides a file system interface where clients can create, update, read and delete files. So let's see the two types. First one is transaction servers. It's also called query server systems or SQL server systems, and in which clients send requests to the server, this particular server, and transactions are executed at the server and the results are shipped back to this client. So this is the basic operations in transaction servers. Then requests are usually specified in SQL and are communicated to the server through a remote procedure call or RPC call mechanism. And transactional RPC allows many RPC calls to form a transaction. Open Database Connectivity or ODBC is a C language application program interface standard for Microsoft connecting to a server, sending SQL requests and receiving results. And JDBC is a similar standard like ODBC that is used in Java programming. Next, let's see the transaction server process structure. A typical transaction server consists of multiple processors accessing data in shared memory, and these processes include server processes. These server processes receive user queries or transactions, then execute them and send results back. And these processes may be multi-threaded, allowing a single process to execute several user queries concurrently. Typically, multiple multi-threaded server processes are executed at once. Then the next is a log manager processes. This process implements log manager functionality, which includes log grant, log release, and deadlock detection. We will see in detail later. Then database writer processes. These database writer processes output modified buffer blocks to disk continuously. Then we have log writer processes. These server processes simply add log records to the log recorder buffer, and log writer process outputs log records to a stable storage, that means a secondary storage. Then we have checkpoint processes. This performs periodic checkpoints. We have processes monitor processes. These process monitor processes monitors other processes and takes recovery actions if any of the other processes fail. For example, aborting any transaction being executed by a server process and restarting it, etc. Let's see the figure where you can see all these processes in a transaction database system or transaction server system. As we can see in the figure, shared memory contains shared data, which include buffer pool, log table, log buffer, cached query plans, and these cached query plans are reused if same queries are submitted again. And all database processes can access shared memory. To ensure that no two processes are accessing the same data structure at the same time, database systems implement mutual exclusion using either operating system semaphores or atomic instructions such as test and set. To avoid overhead of inter-processes communication for log request or grant, each database process operates directly on the log table instead of sending the request to log manager process. Even though it is not done through log manager process, the log manager process is still used for deadlock detection in the system. Data servers. Data server systems are used in local area networks where there is a high-speed connection between the clients and server. The client machines are comparable in processing power to the server machine, and the tasks to be executed are computation intensive. In such an environment, it makes sense to ship data to the client machine to perform all processing at the client machine and then to ship the data back to the server machine. There are some interesting issues related to data servers. That issues include page shipping versus item shipping, locking, data caching, and log caching. So let's see the first one, page shipping versus item shipping. So the smaller the unit of shipping, that makes more messages, that makes more overheading. Okay. So if you want to ship an item, a single item, say a single tuple, and we have to make all those arrangements for the shipping of data from one point to another, and if more items are there, means more messages are needed for these processes. In case of page shipping, which is a type of prefetching, where we can add related items to a single ship, such that we'll have the requested item and all those items that will be accessed in the near future. Kind of prefetching, which can reduce the overhead of transportation. Then next issue arises with the logging. All those items which are page shipped will have implicit log granted to the receiver, but that can cause issues if all these items are not used by the receiving end. certain items which may be requested by other processes, which are unnecessarily waiting till the lock is released by the receiver, even if the receiver is not using all these items. So there are mechanisms that can give back or ship back the locks which are not used by the system. So it's a de-escalation of the lock system which can actually transfer back the locks to other clients who are waiting for the items which are locked unnecessarily by the previous shipping. Next is data caching. Data that are shipped to a client on behalf of the transaction can be cached at the client even after the transaction completes if sufficient storage space is available. Okay, so successive transactions at the same client may be able to make use of the cache data. However, cache coherency is an issue. Even if a transaction finds cache data, it must make sure that those data are up to date, since they may have been updated by a different client after they were cached. So there's a message must still be exchanged with the server to check validity of the data and to acquire a lock on the data. Lock caching. In case of systems where the data is partitioned among the clients and the clients rarely ask that locks on the data, the locks can be retained by the client system even in between transactions. So transactions can acquire cached locks locally without contacting the server, so that they can use the locally cached data with the lock. But the server must keep track of all these cached logs. Okay. If the server calls back logs from clients when it receives conflicting log request, so if any other clients request for the log which is also already cached by another client, the server calls back the logs. Okay, if no local transaction is using it, of course. This thing is similar to the de-escalation of log, but it is done across transactions. That is the difference. Okay, that concludes the first part where we discussed about database system architecture, that included centralized system architecture, client server system architecture, and server systems. Okay, then we will continue with the parallel systems in the next class. Thank you.